Welcome to this lecture series in real analysis. In this lecture, we look at a popular puzzle which is around the notion of exponentiation of positive reals by arbitrary reals. And we discussed this at length in the previous lecture. So if a is a positive real and x is some arbitrary real number, then we defined a to the power x as the limit of such things. Limit of such a thing where Rn is any sequence of rational numbers converging to x, right? And we showed that this limit exists. And even before getting there, we first defined what is meant by a to the power a rational. So all of that discussion happened, and I don't want to repeat it. The upshot is we found this to be true, and that is the key takeaway. So with that, let's move on. And here is our main lemma. This is what we want to discuss. So suppose Euler's number, which is the exponential of 1, is at most a and is strictly less than x. So if this happens, then we want to show that this happens. Right? It's not obvious why this should be true. But first we will give an intuitive explanation of it, and then we will also look at a formal proof. There may be many ways of doing it, but I think the intuitive explanation that we are going to offer is of value. It really shows why this is true, because it is geometric in nature. Okay, so first let's mark out these 3 points on the real line. And yeah, this is the logarithmic curve. This is the graph of the natural logarithmic function. So before we say anything, we first will comment on the behavior of the logarithmic function around the Euler's number. So first of all, what is the value of the logarithmic function at e? Log of e is log of x of 1, but log is the inverse of exponential, so this is 1. So this value is equal to 1. Right. And we claim that the line joining the origin and this point is tangent to the logarithmic curve. I hope the claim is clear. So what is the slope of this line? What is the slope of the line joining this point and the origin? It is this length divided by that length, but this is equal to 1 as we just showed, and this is e. So the slope of this line is 1 upon e. What is the slope of the tangent to the logarithmic curve at the point e? Well, since the derivative of the log is 1 upon x, it shows or implies that the derivative at e is 1 upon e. So the slope of the tangent to the log at e matches with the slope of this line, and that shows our claim that this line is tangent to the logarithmic curve. So in a sense, this is sitting below that tangent line, or it's sitting below this line through the origin and through this point. And from the picture, it is clear that if we draw these 2 lines, they will have lesser slope, successively lesser slope than this one. Right? So this is the tangent line that we just discussed. And if we draw these 2 lines, the line corresponding to the point A and the line corresponding to the point B, their slopes will successively decrease. That is clear from the picture. That has to be argued formally, that's another thing. But that's clear from the picture. So we have that the slope corresponding to the point A dominates or exceeds the slope corresponding to the point B. Right? Which is to say what? What is this? What is the slope? This slope is nothing but this divided by that, which is log A upon A, and similarly, the slope corresponding to B is log B upon B, which is equivalent to B log A greater than A log B. And here is one small claim. If x and y are positive reals, then log of x to the power y is y log x. We know this to be true already if y were a natural number, right? Log of x to the power n is n times log x. That's clear. But we are saying it is generalized. And the reasoning is the reason is very simple, because by what we recalled in the beginning, x to the power y is nothing but x of y log x, right? X to the power y is that, and now log and x are inverses of each other, so therefore all that survives is y log x equal to. So now using that chain, what is this? This is equal to log of a to the power b, and the other thing is log of b to the power a. But log is a monotonically increasing function. Its derivative is always positive, so it's a monotonically increasing function, and hence we have this inequality. So this is the intuitive justification, but there is a formal proof here if you want. You can pause the video and read it. Okay. Before we leave, there is a number theoretic version of this question. Suppose x and y are natural numbers. How many such pairs, how many pairs of natural numbers satisfy this equation is the question. Right? It's a natural number theoretic question. And this has nothing to do with real analysis, right? It's purely a question about integers, in fact, natural numbers. So it's a natural inquiry, and we will use what we just proved to answer this. So so before we continue, we may log assume that x is less than y, and as we just saw, if x exceeds the Euler's number, or is at least the Euler's number, then x to the power y will be greater than y to the power x. That's what we just proved. So for equality to happen, we cannot have this. So therefore, if equality happens, we must have that x is at most Euler's number. But we know Euler's number is at most 2.8. It is 2.7 something, as we saw in a previous lecture. So therefore, we must have x at most 2, because x is after all a natural number. So there are only two possibilities for x. Case 1 is that x is equal to 1. If x is equal to 1, then 1 to the power y equals y to the power 1. We want to see how many natural numbers are there which satisfy this, but there is exactly one natural number which satisfies this. So this means y is equal to 1. So one such solution, we've just found one solution, which is x equals to 1 and y equals to 1. Clearly that is a solution to this equation. And the other case is case 2, x is equal to 2. So we are trying to find out all the natural numbers y such that this holds. Now note that there cannot be too many solutions to this. Why? Because this is a very fast increasing function. What is this? This is the exponential of y log 2. Now exponential function dominates any polynomial, right? Ultimately, this is what we saw. It beats any polynomial. And here we have the exponential function, although it has been scaled a little bit in its input. Doesn't matter. It will still beat any polynomial, namely y square. So for sufficiently large y, we will have this inequality. That we know. So there cannot be too many solutions. And I do not want to argue this in too much detail. Here is a pictorial way to get at all the solutions that you can get here. So y square looks something like that. Something like that. And 2 to the power y, it will take the value 1 at 0, and at 2, these two things will be equal. If y is equal to 2, then this is 4 and that is 4. And when y is equal to 4, then both are 16. So it will look something like that. I mean, there is just no way to draw it really. Maybe I'll put the one below. So it will be sort of something like that. I hope I'm able to convey the idea. The exponential of 2, it will first cut this quadratic, go below, remain below for some time, but at 4 it will cut again, and then there is no coming back. This will completely beat the quadratic polynomial. So here there are only two solutions. I encourage you to, work this out for yourself as to why exactly. So there are only two solutions here, namely y is equal to 2 and 4. So x equals 2, y equals 2, x equals 2, y equals 4. There are only three solutions to this equation in natural numbers. Okay, so this is all that I wanted to say. As usual, like, comment, share, subscribe, and I will see you next time.